Hello and welcome back. My name is Dr. Mark Taylor. This is the Delaware Tech Physics 111 Lesson 6, Part 3. This is part of the third lesson of Unit 2 on forces and energy, and it's a continuation of the section on forces Part 3, which includes work and power. And in fact, this is where we left off at the beginning of the discussion on work and power. So work is a method of transferring energy. Work is one method, heat is another method of transferring energy. But it's very important to mention this right in the beginning, that in physics, the word work has a very specific meaning. It's completely different from the way we use the word work in everyday English. So in physics, work requires two things to happen. It requires a force to act on one object, and it has to result in the displacement of that object. The object has to move. We're going to use D for displacement. I know we usually use delta X for displacement or delta Y, but for now we're just going to simplify it to the letter D for displacement because we're really concerned about the distance an object is traveling when a force is acting on it. So work is a measure of energy transferred to an object or from an object when that object has a force acting on it and it moves. It has to move. No matter what the force is, it has to have some displacement. So as far as the force goes, the force that we're interested in is not just simply any force acting on an object. It has to be the component of the force that's in the same direction as the movement, as the displacement. And as we start looking at examples of when force is happening, it'll be much more obvious what force or what component force we're talking about for each situation. So another way to say what work is work is when a force acts on an object and is displaced. This is how energy is actually transferred, and we measure work in units similar to what we measure energy in when we get to energy. And that unit is called the joule. And we'll talk about that a little later. I'll scroll this up a little bit. The calculation for work looks a little confusing, and you see this cosine function in there, and you think, we're not supposed to have trigonometry. You're not going to have trigonometry. Don't worry, we're going to give you simplified versions of this situation. But the actual formula for work is the force component in the direction of the work. So even if the force is not pointing in exactly the same way that the object is moving, we have to figure out just the force that is in the same direction as movement, or the force component that's in the same direction as movement. And then you multiply that force times the distance the object is actually displaced. In other words, the displacement. So here is our formula in words. The work is the component force. It's in the same direction as the work, as the movement, times the distance the object is displaced. All right, so what do you do if the force is at an angle, or the force is just not in the same direction as the movement of the object? So here we have some object with mass m, and it has to be displaced by a distance d. I know we're using d for displacement, but it's really the same as distance in these cases, so we just use simply d instead of the delta x you might be used to. All right, and if you have this force at an angle, you really need to determine just the force that's in the right direction. And that requires trigonometry. Here's the formula, but we're not going to do that in this class. We're not going to use trigonometry to calculate the component of force that is horizontal if the box is moving horizontally, or we're not going to calculate the force that's vertical if the box is moving vertically. So yes, the actual formula, when you take the force in the right direction times the distance, you end up with this equation: force that work equals force times distance times the cosine of theta, theta being this angle above the horizon that the force is pulling. Now, in your case, we're going to always give you forces, and one of those forces will be in exactly the same direction as the displacement, and you won't have to ever use this version of the formula, and it will always just simply be select the correct force. There might be more than one force showing in the diagram, times the distance, and it's as simple as that. Force times distance equals work, and we're not going to worry about these angles and the calculations from that. So here's the big simplification for calculating these energies. And you'll see there are two examples in these pictures. The example on the left, the object with a mass m is moving to the right, and the force happens to be pulling to the right. And then in the second case, you have a mass m, and the object is being lifted up vertically, again, by a distance d, but this time that distance is actually a height because you're moving up. We just call it a height instead of a distance. And you're going to be using a force to lift it up. Well, when you're lifting an object, the force you have to lift it with has to be the same as the weight of that object. If the object weighs 500 newtons, you have to put a force of 500 newtons to lift it up. So vertical work is really quite easy to figure out. You just figure out what's the weight of the object, because that's the amount of force you have to impart on the object to lift it up, times how high you're lifting it. So the equation F times D just becomes force due to weight times the height. And the force of weight, we already know, is m times g. So if you're not given the weight directly, if you're given the weight directly, you just multiply it by the height. If you're not given the weight directly, you calculate the weight, m times g, and then multiply it by the height. And it's a pretty straightforward formula, and that's shown right here and right here. So horizontal motion, you're not putting a force that's equal to the weight. You have to use some other force because you're not lifting it up. You're pushing it to the right or pushing it to the left. But when you're moving straight up, you're fighting the weight force. So the force you have to put in is going to be exactly equal to the weight of that object. Now, work, it turns out, is a scalar quantity, okay? It does not require direction. However, you can have positive and negative work. It's just not referring to the direction of the work. It's referring to whether the work is being done on an object or by an object, because work is a transfer of energy from one thing imparting the force to the other thing being moved by the force. So the object is moving because force was acting on it. That will be a positive work, and the thing that did the work will have experienced a negative work because it's losing energy. So the object that's moving gains energy. The object that did the work has lost energy. All right. And as I mentioned before, the unit for work is going to be the same unit we're going to see when we do energy, and that is a unit called the joule. And the joule is abbreviated with a capital J, and the joule is just equal to a Newton times a meter. So remember, what is work? Work is force times distance. Force is in newtons, distance is in meters, and when you multiply them together, you get Newton meters, but we have a name for Newton meters. We call that a joule. So work and heat and all forms of energy that we're going to talk about are measured in joules. So work and heat are two ways of transferring energy, and then we have various forms of energy. All of those will be using joules as a unit of measure. Now, I realize most of you are not used to using metric units or SI units, so you don't always have an idea of how big certain things are. So let's talk about just how big a joule is. So the unit of energy is a joule. The unit of transfer of energy, like work and heat, is also joule. How big is it? Well, a newton is a small amount of force. 1 newton is a small amount of force. That's about the weight of an apple. So it's the force required to lift an apple. A joule is a small amount of work. It's the amount of work to lift an apple up 1 meter. How big is a meter? A meter is a little bit bigger than a yard. So imagine having an apple on the ground and lifting it up just a little above 3 feet. That's a joule worth of energy that you had to use to lift the apple up. Okay, lifting 10 pounds up 5 feet, now you're talking about 1,000 joules. Walking slowly for 30 minutes, that's about 500,000 joules. Energy from a regular sized candy bar. I don't know if they still make regular sized candy bars. They keep getting smaller and smaller, but that would be about 1,000,000 joules. So you have to do a lot of work in everyday life to burn off 1,000,000 joules. The energy from a 2-liter bottle of soda, and I know a number of you drink 2-liter bottles of soda all the time, it's over 3 million joules. And you might not be aware of this, but when you read packages of food, they'll say how many calories are on the package. The calories that are on the package are what we call a big C calorie. They have a capital C on the calorie. Chemists use the little c calorie, which is 1,000 times smaller. So this number of joules works out to about 800,000 real calories, the little c calories, but that would be equivalent on a package of food of 800 big C calories. So the big C calories are 1,000 little c calories. So if you're used to counting calories, this works out to about 800 calories. That's an enormous amount of calories, considering that's about 1/3 of what you should be taking in every day in calories, maybe even more than 1/3. Otherwise, you end up storing those calories away in fat and things you don't want to store it as in your body. All right, so here's some work concepts we should discuss. Number 1, is work done when force is perpendicular to displacement? Okay, what am I talking about here? Well, let's say you have a box, has mass m, and you want it to go this distance. You want it to go that far. Well, you could use a force that's in the same direction, but what happens if you use a force that's perpendicular? What if you use a force like that's perpendicular to the direction you want to move? You can't do any work that way. There is no component of this that's going this direction. If I had a force that was at an angle, you could say, okay, well, that angle has a little bit of component force in this direction and a little bit in this direction, and I don't care about this direction. I really care about this direction because that's where I want to go. But vertical forces cannot contribute to horizontal movement. They are completely perpendicular and they have no component in the right direction. Number 2, is work done when there is no displacement? In other words, you push and you push and you push and the object doesn't move. You're pushing on a giant piece of furniture or refrigerator or something, a large rock, and you're pushing for 20 minutes and you're using all your energy. Are you doing any work on the rock? No, the rock or the furniture did not move. There is zero displacement, therefore there is zero work. You can't get anything done. And then the third one is a little trickier, and it's a concept you should know, but you're not going to be directly tested on it, is work done when there's no acceleration. Well, we know from previous conversations about forces and acceleration, if you have a net force, then you will have an acceleration because net force equals mass times acceleration. If you have an acceleration, you have a net force. If you have a net force, you have an acceleration. If there's no acceleration, that means there's no net force on the object you're moving, and therefore there is zero work. So remember, work is equal to the force in the right direction times the distance you're traveling, the displacement. You're moving this object. If there's no force in the right direction, there's no work. If there's no distance, no displacement, there's no work. If there's no acceleration, there's no force, and therefore there's no work. All three of these result in no work. So it's important to determine whether the work is done by just one particular force or the net force is done, the net work is done by the net force, the sum of forces. So you have to look at various forces. Now I'm going to tell you, for the problems you're going to get, there are almost always going to be situations where there's one force that you have to be concerned with, and you can disregard other forces. You just have to look for the force in the correct direction, in the direction of movement, in the direction of displacement. And I have a little note here that says individual forces like applied force or tension force or friction force, these can each do work. So let's say I had a block and I'm pulling it with a certain amount of tension on it, and I've got this tension force, and that's due to me using an applied force, and then you have a friction force backwards, and there might be a weight force down, and there's a normal force up. You have a lot of forces involved. Well, if the object is moving this way, we can disregard the perpendicular ones. They're not going to do any work. But the friction is doing work in the opposite direction, and the tension or the applied force is doing work in the forward direction. So you have different amounts of work. If you really want to determine the work, you actually have to figure out the total forces, which is what we call the net force in the horizontal direction, or the sum of the forces in the horizontal direction, and you use that. Now, we're not going to give you problems that difficult. There'll be one force you're looking for. Okay, so here are just a few examples of work listed here with little bullet points. A person holding a bag of groceries. Is that work? Well, they're holding the bag, they're lifting the bag against gravity, but they're not moving it anywhere. So there's no displacement, even though they're putting a force to hold it up. There's no displacement, so there's no work. A shopper pushing a cart down an aisle at a steady rate. Steady rate means a constant velocity. Constant velocity means no acceleration. No acceleration means no force, and therefore you can't have work. An evenly matched tug of war. So two teams are pulling on a rope. You already know they exert the same force on the rope because the tension is exactly the same everywhere along the rope, and it's in both directions everywhere along the rope. So that force is going to be the same all the way through. The real work is how much force they put on the ground to beat the other team. They're pushing against the ground with friction force to try to pull the other team. But they're not doing any work on the rope, because if they're evenly matched, neither team is winning and they're not going anywhere. So there's zero displacement in those situations. An engine moving a car at a constant speed. A constant speed, again, if it's constant velocity, if velocity is constant, this goes back to the 5 things I told you about. Velocity is constant, the acceleration is 0, which means the force is 0. And if the force is 0, the work is 0 also. Okay, before we start doing problems with work, we have a few other topics that are related to work we should cover. I'll just scroll down. And here we go. So the first of these topics is called Ideal Mechanical Advantage, or IMA. IMA is a number that tells us how much a machine helps us do work. So consider the fact that if you do the same job in a couple different ways, with a machine, without a machine, the amount of work necessary to do the job is the same amount of work. Your work that you do by yourself or the work the machine does is going to be the same amount of work. There's just no getting around that. The input work and the output work will be the same number, at least in theory. So you're going to put in a certain amount of energy, and the machine will put out a certain amount of energy, and those should be the same amount, assuming the machine is 100% efficient. And we'll get to that later. And many machines, especially simple machines like pulleys and ramps and screws and wedges, and they make our lives easier by letting us use less force, but the trade-off is we have to use that force, that smaller amount of force, for a greater distance in order to complete the same job. For example, with a ramp, you could lift a heavy weight straight up, and that would require a lot of force, and you're only lifting it a small distance, but that's pretty hard to do. But if you have a ramp, you can push it up a long ramp with a large distance, but you can use less force as you push up this long ramp. Using a complex pulley system, you can use less force to lift something that might be quite heavy, might be too heavy for you to normally lift, and you use a complex pulley that makes the force a lot less that you have to use. But the problem is, if you want to lift it up, you have to pull a lot of rope on the pulley to make the object move up a little bit. So the trade-off is, if you have a machine that lets you use less force, you have to use more distance in some way when you're applying that force. And that force times distance, when it's a small force and a large distance, will be the same amount of work as if you're using a large force and a small distance, which is typically what the machine would be able to do for you. Well, if you take this formula of a small force times a large distance equals a large force times a small distance, and remember that the small force and the large distance, that's your input, and then the machine's output is the larger force and the smaller distance. Well, if you have this formula, force input times distance input equals force output times distance output, the one in a box here, you can just rearrange this equation, and you're going to end up with this new equation right here that is basically two ratios. Input distance over output distance equals output force over input force. So you notice they're reversed from each other. Well, these two ratios are a constant called the ideal mechanical advantage, IMA. So the IMA is equal to both of them. You can use a formula, IMA equals the input distance over the output distance. In other words, the amount of distance you have to put in, which is going to be large. You have to pull a lot of rope on a pulley or push something up a long ramp with a large distance. That's your input distance divided by what you get out of it. The object is lifted up a certain height. That's going to be a smaller value. So this ratio tends to be a number bigger than 1. It might be 2 or 4 or 8 or 7.3, but bigger than 1. And that same ratio, IMA, is also the ratio of the forces, but now the output and input are reversed. It's the output force divided by the input force. In other words, you get a lot out of the machine relative to what you are able to put in using that machine. You can only use a certain amount of force on a pulley. You can only use a certain amount of force on a ramp, pushing an object up a ramp, but you get a lot of force out of it. The weight force of the object you're lifting might be much heavier. So you get this ratio. And these ratios, since they're ratios of distance to distance or force to force, the units will cancel each other. So IMA is a unitless value. It has no unit at all. Just like what you saw with the coefficient of friction, that's a ratio of the friction force to the normal force, force to force, so those units cancel too. So IMA has no unit, but the IMA is a number that gives you an idea of how much the machine will help you. It tells you how much less force you have to use, and it tells you how much more distance you have to input when you're using that smaller force. So, for example, if you had a pulley and it had an IMA of 4, that means you can use 4 times less force than you need to lift something, but you have to pull 4 times more rope. Likewise, if you had a ramp that had an IMA of 10, that means you can use 10 times less force than you would if you were just lifting an object directly straight up, but you have to push it 10 times more distance than the distance you're lifting it. In other words, you have a really, really long ramp that's 10 times longer than it is high. So you're pushing something up this long ramp and it only lifts it up a certain height, but you push 10 times more of that distance. But luckily, you only had to use a tenth of the force to lift up that weight. So it's a trade-off here, more distance so that you can use less force. So here are a couple examples. A complex pulley might let us use 1/4 of the force to lift a weight, but we would have to pull 4 meters of rope to lift the weight only 1 meter high. Less force than the weight, but more rope. We use 4 times less force, but we had to pull 4 times more rope. Okay, so if this thing weighed 1,000 newtons, you only have to use 1/4 of that force to pull on the pulley. 1/4 of 1,000 newtons would be 250 newtons, but you'd have to pull a lot of rope to get it to go up only a little bit. Number 2 says we might use a 100-meter long ramp to lift a 5,000 Newton weight up a height of 10 meters. Okay, 5,000 newtons is a really heavy weight. A human being would be very stressed to lift something that gigantic. But using a ramp, you could just push it up the ramp. So this would allow us to quote unquote lift the 5,000 Newton object up 10 meters, but you're doing it by pushing it up a 100-meter long ramp. So it's a long ramp that's only 10 meters high, but it's 100 meters long. But you get to use 1/10 of the force. In other words, you get to use only 500 newtons of force to push this 5,000 Newton weight up. And when you're done, the 5,000 Newton weight will have been lifted up a total of 10 meters. So the downside is we have to push it for 100 meters to get it to lift up 10 meters. We get to use 10 times less force, but we had to push it 10 times further than we actually lifted it up. All right. Another topic we need to cover is efficiency. So this is a real world percentage for a machine. What does that mean? Well, very few machines that you use in your life are 100% efficient. In other words, a certain amount of energy is pumped in to make the machine work, and then it puts out a certain amount of energy or a certain amount of work, and it's rarely the same amount of energy. You usually lose some energy, typically in heat. In fact, the only machines that I can think of right offhand that are 100% efficient are heaters, space heaters and other types of heaters, because all of the electricity, when you plug it in, all that electrical energy that goes into the heater, all of it gets turned into heat eventually. So they're pretty much 100% efficient. But just about every other device you use, a blender, even a toaster that's producing heat, a refrigerator, a lawnmower, everything is a little less than 100% efficient. So the ideal mechanical advantage is just that, quote, ideal. It's only exactly true if the machine is 100% efficient. Now, if the machine is not 100% efficient, you might want to make a calculation about how efficient it is, Or you might want to make a calculation if you knew the efficiency, how much work you have to put in to get a certain amount of work out. So the work output of the machine is almost always going to be lower than the work input because most machines lose some energy in the form of heat. Now, so if you want to calculate the percent efficiency of machine, it's actually pretty easy if you know how much energy you put in and how much energy you got out, how much work you put in and how much work came out of the machine. You literally just divide the amount of work that you got out, which is going to be less than the work you're putting in. So the top number, the numerator, is going to be a smaller number than the denominator. And then you're going to turn that into a percentage by just multiplying it by 100%. And that will give you the percent efficiency of a machine. It could be as high as 98%, but that's pretty rare. Or it could be as low as less than 1%. The old classic light bulbs that we used to screw in, and the incandescent light bulbs before they had the modern LED bulbs and some of the other light bulbs out there, those light bulbs were only about 2 or 3% efficient. In other words, if you looked at all the electrical energy that went into lighting a light bulb, only 2 or 3% of that energy was turned into light. The rest of it was wasted into heat. All right, now what if you already know the efficiency? We're going to use this last formula. This last formula is just the same as the upper formula here, just rearranged. So if you know the efficiency and you want to figure out, say, how much input work you have to put in to get a certain amount of output, well, it's the percent efficiency that you might know for that machine times how much work you have to put in equals 100% times the work you will get out. So if you knew the work output, you could easily calculate how much input work you have to put in, and vice versa. Now, power is another thing we need to consider calculating. And in everyday English, people frequently use work and power or energy and power to mean the same thing, but power is actually quite different. Work is what you're doing. It's the job you're doing. You're moving an object from one location to another using a force. Power is how much work energy is transferred per time, or you can think of the amount of energy per time that is necessary to do a particular job. So power is work energy per time. We have to just divide the work by time. It's as simple as that. So you would calculate the work by multiplying force times distance or displacement, and then just divide it by time to get the power. And this assumes that the force is in the right direction. It's in the same direction as the movement. So we're not going to use cosine theta in here. That's for a more advanced course. So power being a rate of use of energy, it's the energy per time that the energy is being used or the work is being done. The units of power are the watt, and the watt is going to be equal to the units of energy divided by the units of time. The units of energy or transfer of energy, like work, is a joule. So joules per second is a watt. So a watt is our unit of power. Now, this is a more advanced section, but it's a pretty straightforward one to explain. It looks complicated because you see a lot of formulas, but I'm gonna prove to you it's actually much simpler than you think it is. So you have the simplified formula for power. It's the amount of work per time, work divided by time. Simple as that. So I'm just going to rewrite work divided by time and substitute for work F times D, the force times the displacement. So now we have that the power equals this value. Well, if power is equal to that, F times D divided by T, I can just move the F out of the fraction, and now we have F times D divided by T. Well, D divided by T, that's displacement divided by T. Displacement divided by T is just the average velocity. So you have the second formula for power. Here's your main formula for power. It's work divided by time. But you also have this other formula, and it's in your formula sheet, that power is the force you are using in the direction that you're moving something times the average velocity that the object will move once you're putting a force on it. It's pretty much as simple as that. So let's look at some work and power practice problems. Number one, a 50 kilogram crate, okay, that's the mass, is pulled by a horizontal force of 850 newtons for a distance of 36 meters. That's your displacement. How much work energy is required? All right. So you have this object and you're moving it horizontally. Now remember, whenever you're calculating work is equal to the force in the direction of the movement times the distance it will be moved, the displacement will be moved. So in this case, you'll notice you're given the number of kilograms, and your first impulse might be, well, you always told me if I have a mass, calculate the weight. If I have a weight, calculate the mass. Well, in this case, you don't need to, because you are told exactly what force you're going to be using and exactly what distance that object is going to be moved in. And the weight force is down. So if you wanted to lift it up, then you'd need to know the weight of the object. But we're not lifting it up. We're moving it horizontally. So we need to know the horizontal force, not the vertical force in this case. So work is going to be equal to the force in the direction we're interested in times the distance it's moving, which is the displacement. In this case, that's the applied force times the distance, and that equals 850 newtons times 36 meters. We plug that into a calculator, and we get 30,600, and if you look at the units, Newton meters. Well, we don't use Newton meters for energy. If you see Newton meters, that is the equivalent of a joule, and joule is what we use for work, which is a form of transferring energy, but we use joules for any kind of energy or any kind of transfer of energy. So it's 30,600 joules. All right, number two, a 225 Newton weight, so that is the weight of the object, needs to be lifted vertically to 8 meters high. How much work energy is required? Well, in this case, you're lifting the object straight up. And if you're lifting the object straight up, you have to lift it with a force that is enough to balance the weight force. You have to lift it with the same force that is equivalent to the weight. Well, the weight is given to you. It's 225 newtons. Now, if you were given a mass in this case, remember, if you were given a mass, you'd have to figure out that the weight is equal to the mass times gravity. But we're not going to do that because we were given the weight directly. And we were given the displacement in the question. So we use the same work formula. It's equal to the force times the distance. But now the force that we're interested in is a vertical force that happens to be exactly equal to the weight. And that's times a distance that's vertically, well, vertical distances, we tend to just call them height. So we can call this h. Now you don't have to change these letters, sorry, that's a dot, to these letters. It's the same thing. I'm just showing you that the specific force and the specific distance can be called other things. But we're going to plug these numbers in. We have a weight force that we're fighting against, that we're lifting up, 225 newtons, and a height of 8 meters. And when we plug this into our calculator, we get an even 1,800 joules, 1,800 joules. And that's the energy. Now, let's look at number 3. Number 3 is interesting because now instead of lifting it straight up like we just did in problem number 2, we're taking the same 225 Newton weight, and now we're actually using a ramp to help us. We need to lift it to 8 meters high again. That didn't change. It's still 8 meters high, and it's still a 225 Newton weight we're trying to get up there. But now we're using a very long ramp, a ramp that is 96 meters long. So instead of lifting it up 8 meters, we are pushing it up 96 meters. That is, the ramp is 8 meters high, but the incline itself is 96 meters. The question says, what is the ideal mechanical advantage of the ramp in question? Well, let me explain the term ideal first. Ideal in the ideal mechanical advantage means if this tool, if this machine, and I know we don't think of ramps as machines, this is referred to as a simple machine. Ramps, wedges, screws, wheels, and axles, these are all considered simple machines that other machines are built of combinations of. All right, so when you have a machine of any type, that machine, if it was 100% efficient, in other words, if it didn't waste any energy at all, if all the energy you put into the machine came out of the machine, that would be an ideal machine, a 100% efficient machine. So we're going to assume this ramp is 100% efficient. In other words, we're not going to lose energy to heat because of friction or whatever other reason might cause heat. We're going to assume this ramp is working perfectly, and all the work energy I put into it is going to be exactly equal to all the energy I get out of it. So the ideal mechanical advantage tells you how much easier it is to use the machine than to do the job without the machine. So if I wanted to lift 225 newtons straight up like we did in the previous problem, I could either lift it with a force of 225 newtons straight up for 8 meters, or I could push it up the ramp with a much lower force, but for a much longer distance. So the ideal mechanical advantage is a ratio, and it can be written in two very different ways, but the ratio is exactly the same value of IMA. The ratio is either the distance that you have to input in other words, how much you have to push, or if it's a pulley, how much you have to pull the rope, divided by how much comes out of it. In other words, I have to push it up the ramp a long distance, but it's only going up by a smaller distance. The ratio of those two is the IMA. And if I put those numbers in, the input distance is 96 meters. That's how much I have to push this thing up the ramp. But I'm only going to raise the weight by 8 meters. So it's a ratio of 96 meters to 8 meters. We divide this out and we get 12. And you'll notice the meters cancel the meters. So this 12 has no unit. It's a unitless value. If you want to say 12-fold or 12 times, that's perfectly fine. But 12 is okay to say. So it has a mechanical advantage, an ideal mechanical advantage of 12. Now, there's a second way to calculate the ideal mechanical advantage by using not a ratio of the the ratio of the distances, but a ratio of the forces. And we reverse the word input and output. So it's the force output divided by the force input. It's always the bigger number over the smaller number. Well, we know what the force output is. It's the force that's required to lift 225 newtons. That's 225 newtons of force. That's the output force. We don't know how much force we have to push the object up a long ramp, but we can calculate it because we know from the previous equation that the IMA is 12. Now, everything I'm doing here from this point on is not in this question, but I wanted you to see that while IMA can be calculated two ways, we don't have all the information to do it with the forces. But if we calculate the IMA the way we can do it and get 12, now we can use the IMA and the force output that we know is the 225 newtons. We could use that to calculate the force input. And by rearranging this equation, we find that the force input is equal to the output divided by the IMA. I'll just write out over IMA, which is 225 newtons divided by 12. Well, this works out to only 18.75 newtons. Well, what does this mean? This means that if you needed to lift a 225 newton object straight up 8 meters, you could do it that way using 225 newtons of force straight up for 8 meters, or you could push it up this long ramp for 96 meters, much longer, 12 times more distance, but you get to use 12 times less force, making it much, much easier for most people to do the job. The key part here is actually illustrated in the next question. How much work energy is required with the ramp? Well, if the ramp is 100% efficient, the work that comes out of the ramp will be exactly equal to the work you put in, right? The work you put in is the low force, the input force, times the long distance, the input distance. But the work you get out is the high force, the 225 newtons of weight force, times a short distance. The output distance would be 8 meters up. So these two work energies, these transfers of energy, are exactly equal if the machine is 100% efficient. And we've already calculated how much energy it is to lift something straight up. So we know how much energy we have to put when we use the ramp. It's still 1,800 joules. And you could actually get that same value by taking the force you already calculated and multiplying it times the distance you know you have to push. If you multiply the input force times the input distance, which are these variables here, you will get the same 1,800 joules of work that is performed. Okay, let's scroll down and take a look at number 5. So number 5 says you need to use a machine to perform 2,400 joules of work, 2,400 joules of work. Unfortunately, the machine is not perfect. It only has a 65% efficiency. How much work do you have to put in to get your desired output? Well, first of all, there are only a few kinds of machines that are 100% efficient. Heaters, as I mentioned before, heaters are 100% efficient because all of their energy can be converted into heat. But most other machines have an efficiency that's going to be less than 100%. So what does it mean? It means that the energy you put in, not all of it will be used to perform work by that machine. So in this case, if you're putting in a certain amount of energy, only 65% of that energy will actually be used to perform this 2,400 joules of work. Well, we have a formula for this. We have a formula that equates efficiency and work input and work output. And here's the formula, just to remind you. It's the percent efficiency that the machine actually is times the work you put in, the work input. In other words, only this percent of the work you put in will equal 100% of the work you get out. So the formula literally says exactly what's happening. So now you plug in the numbers you know. We know it's 65% efficient. We have no idea how much work we have to put in to get out our work that we want, but we know that 65% of whatever we put in will become 100% of the 2,400 joules we need to come out of our machine. Well, we divide both sides by 65%. These two numbers will cancel, percents will cancel, and the only unit that will be left is joules. So our work input, in other words, how much work we have to put into the machine to get out, will be 100 times 2,400 joules divided by 65. And when we put this into our calculator, we get that we need to put in 3,692 joules of work. And this makes sense. If we want to get out 2,400 joules of work, we have to put more work in. If you get a number that's less, you have to ask yourself, where did I go wrong in this? Your answer should match when you think about, hey, I'm only going to get 65% of this to become this. So use a little logic to check your answer. Does it make sense? Is the amount I'm putting in bigger than the amount I'm getting out? That makes sense because I'm going to lose some energy to heat. All right. Number 6. Andy uses a force of 500 newtons to move a crate by 50 meters in 25 seconds. Beth uses a force of 400 newtons to move the same crate by 80 meters in 32 seconds. Who did more work? Who used more power? All right. Well, first of all, work is what we need to calculate first. And work is the force in the direction we're going to be using it times the distance or displacement. Well, this is a case where they're moving a crate and you're told how much force they each use. You're told how much distance or displacement they each have to go. And you might be looking at it and saying, well, wait, what about the 25 seconds? Work is independent of how much time there is. Power depends on time. Work does not. So the work for Andy and the work for Beth can be calculated by taking each of their forces, 500 newtons for Andy, 400 newtons for Beth, that's the force they're going to use, times 50 meters for Andy, and 80 meters for Beth. We multiply these out, we get 25,000 joules of work performed by Andy, and we get 32,000 joules of work performed by Beth. Beth used less force, but covered a much bigger displacement. And as a result, her work was greater. So who did more work? The answer is Beth did more work. Part B asks, who used more power? A more humorous way to ask that is, who is more powerful, Andy or Beth? Well, to get power, remember our power formula is work divided by time. Well, they each have their own amount of work, and they each used a different amount of time. So now we plug it in, the power for Andy and the power for Beth. Power for Andy is his 25,000 joules of work divided by the 25 seconds it took him to do that work. And that's equal to 1,000 joules per second, but we use the unit watt, so that's 1,000 watts of power. And watt is abbreviated a capital W. Beth's power is 32,000 joules of work. She had more work, but she did it in slightly more time as well, so 32 seconds. And when we divide this out, we get that she also had a power of 1,000 joules per second, or 1,000 watts. So the answer is Andy and Beth's power are the same. That is, they are equally powerful. All right, there's only one more problem, and it's an advanced problem, so you can stop here, and this would be the end of the regular lesson 6, or you can watch the next video on this advanced problem.